Okay, so welcome everyone. Today is like the second session for the doubt clearing session for the polymer reaction engineering. We'll be looking at a few problems which will be helpful for you to solve your assignments which have been uploaded in the NPTEL course Polymer Reaction Engineering. Uh, I think till assignment 2 has been uploaded, I guess. I think it was uploaded yesterday. So we'll be going through a few questions and if you have any doubts regarding the questions from the previous assignments, assignment 1, or if any of you have gone through the assignment 2, you can ask them. So if I'm audible and if my presentation is visible to you. I guess it should be visible to you. Uh, we'll go through these and let's start the session. I guess mm, if anybody else joins in, I'll try to get them online and then we'll begin. So I'll start right now. Okay. So my name is Rohan Jadhav and I'm the TA for the Polymer Reaction Engineering course, interactive live session, and we'll be going through some problem solving for the assignments on it. So the first question we have here is, what are the monomers? There are the four options here. Largest unit in any polymer, small molecules which combine to form big molecule. The molecular weight of each representing unit should be less than 10 AU, and it is not present in the repeating structure of polymer. So here is a visual representation of what does a monomer mean and how it forms a polymer. So you can see right here that many small molecules, these small beads, they are either linked together through polymerization process to form the one single large molecule that is a polymer. And this linking can either be linear or in any branch manner. So here you can see these monomers are separate. They are linked together in a linear fashion to form a large molecule like this. You can see the straight chain. This straight chain is your linear polymer. Okay. So the straight chain is your linear molecule. And then another example would be that if these were to link together in a branch manner, they would form something like this. This is a cross-linked phenolic resin. So you can see that the monomer here is a phenol group. You can see the benzene ring with an OH attached to it. So these are the phenol groups and see how they are branched together. And you can see the branching orientation of all the phenol groups and how they are substituted. So you can see the substitution types also. The terminal groups are there, branched or linear. Linear in the sense like it goes in a linear fashion, like this large molecule, or in a branched manner. As you can see, this OH, this phenol group is present here, and it is branching two of them, one above and one below it. So it is branching O and one on the left hand side also. So you can see left hand side, top and bottom. There are three groups coming out of this single phenol group. So this is a branch group, and this is a terminal group because it is present at the end of it. So these are also terminal groups. You can see how they are present here. Okay. Mm, I hope I'm audible to you. And yeah, okay. And this was the first question. Next, the function of reactive species R star in any. Hello.
Sharav,
Yeah.
sorry to interrupt. Actually, this slide number two,
Yeah.
we have discussed about the polymer, but whether only one option is it, I believe it is through. Correct, na? Like it is the queries ask the what is the one
Yes.
or the
Yes.
monomers
Yeah. It is the small molecule which is combined to form the big
are
molecule.
correct. Okay, okay.
Yes, that's one. Okay.
You just want to confirm that because
Uh-huh.
actually yesterday it was something when we discussed it was like highlighting the answers also like when
Oh,
we
okay. Okay.
progressed.
Okay. Yeah. Yeah. I'll just yeah, like I was going to explain it. It's fine. Okay.
Okay, fine, fine.
Yeah. Yeah. Okay. So yes, it is the small molecule which is combined to form the big molecule. The second one is the ionize. Okay. Next we have the function of reactive species R star in radical chain polymerization is. So in radical chain polymerization, what happens is your R star group, right? It first initiates the reaction because it's a radical species. What it will do is this is your R star. Okay. So this is your R star. In this case, in this reaction scheme right here, this R star, it goes ahead and attacks the double bond right here and it will break it apart. And then this atom will, you can see the reactive species is joining onto this double bond group and it is breaking it down to a single bond group. which will proceed the reaction with the another formed radical. And this initiated step will then propagate further and further to n number of atoms present inside the double bonds, n number of double bonds which are present inside the solution mixture. That will start forming your polymerization reaction. So this is an addition polymerization reaction, or you can call it radical chain polymerization reaction. So it initiates, then it propagates, and then once all the polymer chains have expanded enough, the end groups, sometimes when they are facing together, uh, when two end groups are facing together, they will join together to terminate the reaction because these not a single chain is proceeding at one time. There are simultaneously many chains proceeding at different times. So when these chains come together, this left hand side is one chain, right hand side is one chain. When they come together, these two will join together to form a single chain, and that will terminate the reaction. Okay, so this will form the termination step. So the function of the reactive species is to initiate the chemical reaction. Okay, it is initiating that is the first step. It is going through the first step, and then it propagates it and then terminates. So initiation of the chemical reaction is the correct. Okay, then the next question we have right here is that what is the meaning of polymers, which is actually quite it's a true or false question. The word polymer means mers and poly of same or different kind and can have complexity in structure and having different mechanical and chemical thermal properties depending upon the monomer units attached in the main chain. So the monomer itself is giving the property to the polymeric chain, and when these monomers are arranged in a linear fashion or in a branch fashion, what happens is that the entire molecule will have a different kind of property which is arising from the individual monomer property. So word polymer means having many mers. Poly means many, and mers is the single unit. So the statement is true. Next is the polymers which melt first time when they are heated, and during the first heating, the polymer is cured, and after that, it does not melt on reheating and degrade after that is called melt. So there are different polymers. There are two kinds of polymers basically, which first kind of polymer is called the thermosetting polymer, and the second is thermoplastic polymer. Now, what does thermosetting mean is? Thermosetting means once they are heated and cured, what happens is during the curing reaction, the polymer molecules, right, they cross-link together. I'm just going back to the previous question to show the image. These monomers, you can see that they form strong cross-link bonds. Once they form the strong cross-link bonds, what happens is the molecular structure of the polymer will start having some rigidity inside. What does rigidity mean is when the polymer molecule is rigid, it means that it is not flexible enough and it cannot move around. So what will happen during that time is that when you first cure the polymer, once it has been cured, it cannot move again. So if you start heating it again, once the cured mixture is cooled down and it is heated again, since there is no way for the polymer change to move, they won't move because of the rigidity. And because of this rigidity, it does not melt. It means that melting essentially for a polymer means that it starts to flow. It starts behaving more liquidy. So because of this rigidity, it won't melt and it will start degrading. Why? It will burn up because it is not able to release that heat which is being stored inside it because of the rigidity. What it will do is it will start burning and it will degrade. So those kinds of polymer are called thermosetting polymers. Okay, because once they are set, once the cured polymer is set, it does not move again, and it is very resistant to thermal fluctuations. Why? Because once the rigidity is compacted into the polymer molecule, you can heat it to like pretty high temperatures and it won't degrade, which means that it won't undergo any deformation, which means they'll be able to withstand high temperatures. For example, your switchboards, they are made up of a material called bakelite. That bakelite is a cross-linked thermosetting polymer. That thermosetting polymer what happens to that is that it will actually be properly set, and it won't melt, because electrical fires usually what they do is electrical fires occur because of some loose connection, and because of that loose connection, uh, extreme amount of heat is generated, and only then the backlight material is melted. So you can see that backlight does not burn automatically on top on its own. Next type is the thermoplastic polymer. The answer for this question is the first one, the thermostatic polymer. But I will still explain what is thermoplastic polymers. So in thermoplastic polymers, what happens is that once you heat the polymer, there is no curing inside this. Okay. For example, polyethylene. Once you heat it, it will start to flow. The chains are free to move because there is no cross-linking involved. So you can see that there is no cross-linking involved. The first case you can see here. These are the long chains, so they can flow around, and they melt and they flow around in a liquidy manner. So because of that, what you can do is once you cool it down, it can change its shape. Okay. So once you heat it, it will become liquid. You can mold it into different kind of materials, and then again you cool it down, it will retain its shape. That is your thermoplastic mold. Now next is elastomers. What are elastomers? Elastomers are materials which even at room temperature, if you stretch them or if you like compress them or stretch them, they will return back to its original shape. For example, rubber. The best example for elastomers is rubber. That is your isoprene or neoprene. Okay, you can that is the molecule for the rubber. What happens with that is you all must have encountered rubber in some way or the other. You can stretch it and we can release it, and it comes back to its original property. That is the elastic behavior of the material. So example for that will be rubber. So the answer for this question is the thermostatic one. Coming on to the next question. Which of the following can be used for impact resistant materials and are also used as thermoplastics, elastomers, compatibilizer, or emulsifiers to create stable blends or alloys? So, so for this, what happens is that we have different kinds of polymerizations, that is graph polymerization, gradient polymerization, statistical or alternative polymerization. One second. So for impact resistant materials and are also used as thermoplastics, elastomers. So for these things, what is the best way is uh, for impact resistant to make impact resistant materials, what you need to do is you need to impart some kind of rigidity to the structure. And to impart that rigidity, you need to have some kind of functional group, or you need to have some kind of other monomer which can impart that property. But at the same time, the main chain should not lose its property. Why? Because it should behave as a thermoplastic or an elastomer, compatibilizer or an emulsifier to create stable blends or alloys. So for that, the best process to use will be graph polymerization. What happens in graph polymerization is you will have a long chain. What you're doing is you're grafting some other molecule on top of it. Okay, so because of this grafting, what is happening is it will provide additional properties to the main linear chain. That grafted molecule, what it will do is if there are series of chains and if you're grafting different molecules at different positions, what they will do is they can either create hydrogen bonding or some kind of interaction between these chains to provide some sort of rigidity which will make the material impact resistant. But at the same time, since the main linear chain of the polymer which was already existing will have its original property as a thermoplastic, elastomer, or all of the above. So for this question, the correct answer is the graph polymerization. Next we have broadly, polymerization can be classified into two categories: step growth or condensation polymerization, and chain growth or addition polymerization. Uh, and then we have statement one. It's a statement-based problem. The classification based on condensation addition relies on polymer composition or structure. Then next we have the classification based on step chain. relies on polymerization mechanism. So the classification based on condensation or addition relies on the polymer composition or the structure. So basically, in condensation polymerization, what happens is when the step growth polymerization or condensation polymerization occurs, it will remove a molecule. Basically, it will form a condensation product, and that condensation product can be water or any other molecule also. So it will be dependent on the composition or the structure also. So in that case, the classification based on the condensation or addition relies on polymer composition or the structure. Statement 2, we have the classification based on the step chain. Step step chain relies on polymerization mechanism. So the chain growth or addition polymerization will rely on the polymerization mechanism. How? Because as the name suggests, each monomer is adding and giving the length to the chain. So step by step, the chain is growing. So we can either, the name itself is quite synonymous, but don't get confused with that. In condensation, we are removing a molecule, and in chain growth, we are adding molecules to make the chain longer. So we can say that statement one will be correct, and two is also correct. Because in condensation polymerization, it is very crucial how the structure of the polymer is. If the structure is having some scope for condensation, it will give you a condensation product. So it depends on the structure of the polymer, how the condensation or the chain growth reaction will proceed. So that's why both statement one and two are correct. Then we have which of the following options is or are correct for the applications of making non-stick coating on utensils. We have polyester, polyethylene, HDP and LDPE, and then we have the polytetrafluoroethylene. So here we have the structures for three of them. We have the polytetrafluoroethylene, then high density polyethylene, and the low density polyethylene. Why is it called low density polyethylene? First of all, is because in low density polyethylene, you can see that there is a lot of branching in the main chain. And because of this branching, the distance between the individual polymer chains is quite far apart. And because of that, the packing density of the polymer chains is quite weak and that it's quite low. So that's why it's called low density polyethylene. In a similar way, why is it called high density polyethylene? Is because the branching is quite minimal, and because of that, the packing of the individual chains is quite proper. You can see how these three chains are close together, whereas these three chains are quite far apart. So that's why it's called high density polyethylene. But we know that since it's a cooking utensil, the temperature is going to be very high. And we know that polyethylene is a thermoplastic polymer, which will lose its form at uh, relatively low temperatures. Relatively low temperatures means for standard of cooking, the gas flame will reach up to maybe 300 or 400 degrees Celsius, maybe even more than that. And HDP and LDP cannot survive that kind of temperature. But we have another material called the tetrafluoroethylene. So you can see here that it's a long chain of uh, four atoms of fluoroethylene combined on a single molecule right here. So if you were to ignore the rest of the chain, and you can write it the short form of it, C bonding C in the bracket with an end right here. That is a single molecule of the tetrafluoroethylene. Why is it called tetra? Because in the single CC bond we have four fluorine atoms. One, two, three, and four. Here there is a chain representation, and you can see that fluorine atoms are present on both sides. Fluorine atoms are very useful in using repellent coatings, water repellent coatings also. Why? Because of the fluorine's electronegativity, very small size and very high electronegativity, it is able to repel the water molecules more efficiently. And that is the exact reason why polytetrafluoroethylene is used in making non-stick coating on utensils. The actually industrial name for this is Teflon. tetrafluoroethylene, or Teflon. So that is the Teflon coating which is used on the non-stick utensils. So I hope everybody is able to follow whatever is being taught right now.
Yes, yeah.
Yeah, okay. So I will proceed now. Have you gone through the assignment two, or only assignment one have you completed?
Week one assignment and week two both are like due for 7 2.
Oh, okay. Okay. 7th, right? 7th February.
Yeah, yeah, yeah.
Okay, okay. So there is a lot of time. Okay.
No, no, actually, because I think we have started bit early. That's why that first week is assignment and this one coming up together.
Okay. Okay. Got it. Got it. I think first week's assignment is not that tough. I would say that you'll be able to find the answers for that easily, right?
Correct. Mostly it would have been submitted by most of the people already.
Hmm. So have you submitted it? Or
Yes,
Neha,
yes,
or
yes.
maybe the other students also who are present in the call right now? Neha or Neha Shri, I guess I'm pronouncing your name right. Okay, I guess you guys might have submitted it. So I will move on to the next question. So moving on to the next question. Which of the following is or are cross-linked polymers? So we have four options here: phenol formaldehyde, bakelite, high-density polyethylene, and urea formaldehyde. So I did not get the structures for the uh, actually the urea formaldehyde because uh, urea formaldehyde and phenol formaldehyde because there was no proper structure, so that I wasn't able to add it. But I got this structure from sorry, the phenol formaldehyde. So we have the structure for the bakelite. This molecule right here is bakelite. So as I told you in the beginning itself, that bakelite is used for making the switch boards for electrical switches to avoid any high temperature fires because bakelite, since it's a cross-linked polymer, as I told in the beginning, bakelite is used for making the switch boards. And yeah, so that is one of the correct answers for this question. But then we have the phenol urea formaldehyde. This structure right here is for the urea formaldehyde. So this is the chain, and how this chain is connected to the others is that first of all, it is formed by condensation polymerization. Next is that the urea formaldehyde, it cross-links from the NH2 groups and the double bond C groups. So it will form a branching, and this CH2 present in the middle also participates in branching. So you can clearly see that they will branch or cross-link together. Branch, or you can say cross-link, to form the bigger molecule. I wasn't able to get the structure for the phenol formaldehyde, but that is also another cross-linked polymer because there was no proper mechanism of the picture for the molecular structure of that. Next, we have the high density polyethylene. So, as we saw in this picture itself, that high density polyethylene is not a branch polymer. So, there is no branching present in this. So, that will be so the correct answer. That won't be the correct answer for this question. So, the correct answer is the phenol formaldehyde, bakelite, and urea formaldehyde. Next, we have the which of the following have a higher melting point? Linear polymers, branch polymers, or the cross-linked polymers. So amongst these, till now we have seen a lot of examples. So we can tell easily that the cross-linked polymers will have the higher melting point. And why is that? Is that because for melting to occur, the polymer chains must flow past each other. So for that flowing past each other, as we saw in the HDP molecule, if I heat this HDP molecule, these are linear chains. Okay. So what will happen upon heating is that they will flow past each other because there is no virtual interaction between the individual polymer chains of the polyethylene high density polymer. So they will flow past each other. Okay. Whereas in a cross-linked polymer, such as the bakelite molecule, which is shown here, this cross-linked polymer, first of all, it is going to be extremely rigid. And because of that rigidity, as I explained in the beginning, it won't deform under high temperature. Whereas another example for the branched polymer would be the LDPE present here. You can see that we have the high branching here. This branching, what uh, what it will result in that is that it is going to reduce the backbone force inside your main molecule. Now, what is the backbone force? Backbone means for this polytetrafluoroethylene or HDPE, you can see that the carbon-carbon bonding, which is present in the linear chain right here, this is called the backbone force of the polymer molecule. Why is it called backbone? Is because you can see this LDPE molecule. You can see how the branching is present right here. So this branching is being held by this main chain, main linear chain. This main linear chain is standing because of the covalent bonds between the carbon atoms. So that covalent bonding is your backbone force of the polymer molecule. Okay. So that is the main force which provides the rigidity or any kind of property to the polymer itself. And then when you add the functional groups to it, it reacts differently. So the polymers basically are formed from the backbone force of the covalent bonding of the carbon atoms. Okay. So for the answer to that question is cross-linked polymers will be having the highest melting point because of the least rigidity in the molecule. Then we have
Just
that.
sorry
Yeah,
to interrupt. Just to clarify, when we were discussing yesterday, there was about that HDPE.
yeah, yeah.
We were told like this will have a cross link also when HDPE is there. Though we are changing, showing it as a linear chain.
Hmm.
Yesterday, the discussion happened. That specific doubt was there, and for the question, it was highlighted. All are having this cross linking that
Oh,
option.
actually, for which question?
Just
Uh,
yeah.
all will be having cross-linking, but that's not possible because high-density polyethylene is not having any cross-link. It will
I
have
got it,
branching.
but yesterday that was one of the query, and when it was discussed, actually the answer flash was all are having this, but it is understood. Yeah, phenol formaldehyde, urea formaldehyde, and bakelite, all this have polyamide or
Yeah,
phenol formaldehyde
yeah,
with the transition reaction means that will have the major like what we can say like cross-linking capability.
yeah. That's what the
Okay,
thing
so
is.
that's what to reconfirm. So which means
Okay.
that other one is not correct. Like HDP is not the correct option.
Yes, yes. HDP is not
Yeah,
at all the correct answer.
yeah, exactly.
Why? Because
Because
see, okay. First of all, I will clarify one thing. It is impossible to make a polymer linear polymer chain with no branching. Like there will be some branching because it's like what should I say? We cannot control the reaction in such a way that we can prevent the branching. Okay, so there are different grades of polyethylene first of all. Okay, starting from the lowest, that is LLDP. LLDP is linear low density polyethylene. So what happens in that is you are minimizing the branching, but still considerable amount of branching is present. That's why it's called linear low density polyethylene because the packing of the individual chains is not good enough. Next, we come to the LDP. Above that is LDP, where considerable branching is there, but the linearity of the chain is not ensured. Okay. After that comes the HDP. In HDP, the polymerization mechanism is focused in such a way that we are reducing the branching, but we are not eliminating it because it is basically impossible to eliminate, right? Because it won't be like we are not trying to like we are trying to get the perfect linear chain, but sometimes like it's not possible to get it. There will be some branches, small amount of branch, but definitely there is no cross linking because that kind of polyethylene is a different polyethylene that is called XLPE. XLPE is cross-linked polyethylene. Okay, that is entirely different. That is not HDP. So HDP will have branching but not cross-link. Remember this. Okay.
yeah, that is clear because that was like yesterday when that point was discussed. It was by mistake. Maybe that was the
Hmm.
information. Yeah, clear. Now it is clear. Yeah,
Okay. Okay. And just for further information, above HDP there is another molecule called UHMWP. That is the ultra high molecular weight polyethylene.
correct, correct. Yeah,
That
yeah.
Yeah, that polyethylene is the one which is having the highest molecular weight of any of the polyethylenes, and it is having the least amount of branching. So that has the perfect linear chains, and the packing density of ultra high molecular weight is even higher than the HDPE. Okay,
Yeah, yeah. Now that radiation resistant composites and all, people are using this with benzoxazine. All
exactly.
right. Yeah,
And even for soft carbon materials.
yeah, yeah, exactly. Yeah.
Yes, the new age soft carbon materials are basically using the ultra high molecular weight. Okay.
Okay. So can you repeat again? What is that application?
Uh, Soft armors, soft
Of
armor, body armors,
okay,
soft
okay,
body
armors,
armors.
body
Yeah,
armors.
yeah,
Okay, clear, clear.
body
Okay,
armors. Yes.
okay, right. Yes.
Okay.
Yeah.
So next these are the last two questions now. First, we have which type of material is generally used for electrical insulating material. So, as I said earlier, thermosetting polymers are the best to handle any kind of electrical fire or high temperatures which are generated during inside the electrical circuits. Okay, and usually the wires itself are made up of thermosetting polymers. Why? Because when you see that when an electrical wire is burned, it smells a lot because it's not melting; it's basically degrading. So that's why it's a thermosetting point. Thermoplastics, elastomers, or any kind of fibers won't work for that. That's why thermosetting polymers are used for the electrical insulating material. And the last question is more of a trivia question. Trivia question in the sense like it's just there to test your uh, maybe historical knowledge or something like that. That the name of the scientist who first introduced the principle of chemical reaction engineering in the polymer reaction processes. That will be Professor Kenneth George Denby. So these were like about 10 questions for interaction. And if you have any doubts in any one of them, you can ask me. Or if you have any doubts in solving your current assignments, that also you can ask me. So that's all for today's session. So if you want to ask any doubt or anything which you have faced during the solving of your uh, current assignments or anything, you can ask me. And if you have no doubt, then we can like end this session. Next week also I'll be coming. Next week will be solving for the assignment two. Maybe there might be some questions in this itself which will be helpful for you in solving assignment two also. Or else I'll be discussing assignment two also in detail. And every week we'll be meeting on Tuesday. And if you have any doubts, you can bring them to me, and I will try to clarify. Or if you thought that any concept was not clear during the class itself, you can ask. Okay?
I have a small request. Probably,
Yeah.
I don't know whether it is like one requirement is like now since we are coming from office after 5.
Okay.
Sometimes it will be helpful, really helpful if we are starting by 7 because yesterday I understand more than 28 people were there for the
Oh,
discussion.
okay. Yeah.
So most of working people are there means straight away starting by 6 it will be really tough. All the people may not be able to join.
Oh, okay.
So it's a
Okay.
request to be. I don't know
Yeah,
about
yeah.
other.
Okay. Then.
Yeah.
I will try. Like, I will be here from around 6 to 8. So I'll
Oh,
be like the session will be on from 6 to 8. So you can join at that time, 7. Okay. It'll be better if you join. Like, it'll be better if you join early itself, 6:45 or 7. Fine.
yeah, sure, sure. Just I was requesting because yesterday we have seen good numbers.
Yeah.
That's why almost 28 people were there during the session.
Oh, okay. Okay. Good. Good.
Maybe most of the
So,
working people it will be difficult. That may be the reason. I just
mhm.
put it that. Yeah.
Okay.
Okay.
That's fine. Yeah. Thank you.
Thank you very much.
Yeah. Yeah. Okay. So, if you don't have any doubts or like all the problems are cleared, you can like if you want, you can leave. It's fine.
Okay. Thank you
Yeah.
so much.
Yes. Okay.